Hello, welcome to the 13th lecture in ML series. In this lecture, we will be discussing why a direct linear regression is not suitable for solving classification problems and how an extension to linear score followed by a special function sigmoid can be helpful in solving classification problems. So let's quickly recap what we discussed in the previous lectures. Given a data set, learning a relationship between variables to predict continuous numerical value where the relationship is a linear, we said it as a linear regression problem. So in those linear regression problem we considered a hypothesis as s theta of x as theta naught plus theta 1 x1 plus theta 2 x2 so on theta 1 xn, where x1 and x2 so on xn are the features which are used to predict the output, and theta naught, theta 1, theta n are the parameters. Now the goal is to find theta naught, theta 1, so on, theta n, which minimizes the mean squared error for a given data set. Now, once we found the parameters which are used to predict some continuous numerical values, predicting house prices, predicting student percentages, so on. Now, what is the classification problem? In case of classification problem, what we are interested in is given a data set, finding a relationship between variables to predict discrete class label, like taking decisions whether a given email is a spam or a not a spam, whether a person is having a disease or a no disease, whether a person passed or failed. If it is a binary classification problem, you typically represent with two classes, class 0 and class 1. So ideally in case of classification problems, what we are interested in is we are interested in giving a probability that an example or an instance belong to a class. So what is the probability of a given instance belongs to class 1 given that instance, that is probability of y is equal to 1 given x. This is what we are interested in. So now first we will try to understand how why a linear regression is not directly suitable for solving a classification problems. So in case of linear regression, we know that the hypothesis is this theta naught plus theta 1 x1 plus theta 2 x2 so on theta n xn. The output range of the linear regression is minus infinity to infinity. When we want a probability, that range should be 0 to 1. So range is not suitable. That is one of the issues. And the other issue is when you have an outlier. When you have an outlier, the linear regression problem is sensitive to outliers. An outlier, when you have some additional training examples which are far from the others, then as we are using a mean squared error, there will be a drastic change in the theta naught to theta 1 values, theta 1 to so on theta n values, which may give incorrect classifications, and which is making the model is unsuitable for the classification task. So what we need is we need a function which squashes its output into probability range. Instead of minus infinity to infinity, we need 0 to 1, and which provide a more robust way to define a decision boundaries. So that is our thing. Like as we just said, linear regression is not suitable for the classification. What we require is we require a function that should output 0 to 1 and which should be less sensitive to outliers and which provide a clear rule for classification decisions. So the solution is sigmoid function, which is also called as a logistic function or a squashing function also, because it squashes the output from 0 to 1. Now the mathematical formula for this sigmoid function is g of z, which is represented with a g of z. G of z is 1 by 1 plus e power minus z, where e is a Euler's number. Now what is the output range? So suppose if we take z as minus infinity to infinity, and it is a continuous function as well as it is continuous function. So when you consider z as minus infinity, if you consider z as minus infinity, then you are going to get 1 by 1 plus e power infinity. E power infinity is infinity, so 1 by infinity is 0. So the minimum value that gz is can take is 0. And when you have when you give z as infinity, you are going to get e power minus infinity, that is 1 by e power infinity, that is 0. So you are going to get 1. So the maximum value is 1. So it lies between the that 0 to 1 probability range, and it is a smooth curve and an S-shaped curve. You can see here, when you have z equal to 0, you are going to get the 0.5, because 1 by 2. Okay, and some more properties like, and one of the important characteristic that should be required is it should be differentiable, because we are going to use in the optimization setting like a gradient descent, where we take the gradient. So now first we will try and it has a nice property. The derivative of that function can be written in terms of the same function. So let us find the derivative. So g dash of h is dou by dou z 1 plus e power minus z power minus 1. This is in the form 1 by x, that is minus 1 by x square. So minus 1 by 1 plus 1 plus e power minus z whole square, and with a chain rule, so you need to find even a derivative for 1 by 1 plus e power minus z. So when you take 1 by minus 1 by 1 plus e power minus z whole square into, so the derivative with 1 with respect to z is 0, and e power minus z is minus e power minus z. So you are going to get minus minus will be cancelled out, so you are going to get e power minus z by 1 plus e power minus z whole square. Now if you add plus 1 and minus 1 here, then you are going to get 1 plus e power minus z minus 1 by, and if you take 1 plus e power minus z by 1 plus e power minus z whole square, you are going to get 1 by, similarly you are going to get minus 1 by 1 plus e power minus z whole square. Now if you observe, 1 by 1 plus e power minus z is nothing but g of z, and this is g of z whole square. When you factor it out, you are going to get g of z into g 1 minus g of z. So that means the derivative can also be written in terms of the same function. This is a beautiful property which is useful in finding the gradients. And another thing is, it is also a nonlinear function. As you can see, it is a nonlinear function from this curve, and which is useful in modeling a complex relations. Okay, now how are we going to use this sigmoid function for a classification? So we are going to change our hypothesis now. So what we do is, we'll combine the linear model with the sigmoid function to produce the probabilities. So that's what your logistic regression. So first we calculate for a given x and a parameters theta naught to theta naught, theta 1, theta 2 to so on, theta n, we calculate the linear score. That linear score we call it as a z. That z will be given as a input to the sigmoid function, or a sigmoid function is applied on that z. Even though z ranges from minus infinity to infinity, this sigmoid function gives an output 0 to 1. So now you have a new hypothesis, that is h theta of x, where z can be written as theta transpose into x. So you are going to get h theta of x as g of theta transpose x, that can be written as h of theta of x as 1 by 1 plus e power minus theta x, and this hypothesis ranges output from 0 to 1. and which can be used for predicting the probabilities. Now, as we can say that the whatever the output that you get from the logical regression hypothesis, we can directly interpret it as what is the probability that it belongs to class 1 given a data point x and parameters. So we will read it as the probability that it outputs as class 1 given a input x and parameters theta. If it is considered as a binary classification problem, then we can also calculate what is the probability that y given y equal to 0 given x and parameters theta, that is 1 minus h theta of x. So this is how one can use to predict the probabilities. Now, so far what we had discussed is linear regression is not suitable for a classification due to its unbounded input minus infinity to infinity and sensitive to the outliers, and then we have defined a sigmoid function that is 1 by 1 plus e power minus z, and which squashes any real input into range 0 to 1 in the range that is required for the probabilities. This is also called as a squashing function, and which provides a smooth S-shaped curve. And in logistic regression, our hypothesis is h theta of x is g of theta transpose x, that is 1 by 1 plus e power minus theta transpose x. So that can be directly used to estimate what is the probability that a given data point belongs to class 1. So now we have found our hypothesis. Now the next question is, for a given data set, what is the cost function that we should choose for a logistic regression, and what kind of an optimizer algorithm that we have to choose to find the parameters. Okay, that is what we will be discussing in the next lecture. Thank you.